write the Taylor series from number 4, which was for ln of 1 plus x near a equals 0 in sigma notation, and find the interval of convergence. So this is the series we found. And what we should notice is that every term is x to a power over that same number, x to a number over that same number. So they all look like x to the n over n, and n would be starting at 1. But then I also have to account for the fact that my signs are alternating. So I've got a -1 to a power that creates alternating signs. I want my first term to be positive, which means I don't want my first exponent to be 1. I want it to be 2. So this would have to be n plus 1. And then to find the interval of convergence, I do the ratio test. So I take the limit as n goes to infinity of the n plus first term over the nth term, and I need to force this limit to be less than 1. So this is the limit as n goes to infinity, absolute value. I'm replacing every single n in this formula with an n plus 1, so I get x to the n plus 1 over n plus 1. And then the -1, I'm just going to not even write down because all of this is an absolute value. The -1 to the n plus 1 just alternates between -1 and 1, and the absolute value of -1 will be 1. So I'm not going to write down the -1 to the n plus 1s here. All right, and then I'm going to divide by the nth term or multiply by its reciprocal and simplify. This is the limit as n goes to infinity of the absolute value. X to the n plus 1 over x to the n simplifies to x. And then I have n over n plus 1 for the n's. And when I take the limit as n goes to infinity, x has nothing to do with that. There are no n's in that factor. So I'm going to pull it right out of the limit. So this is the absolute value of x times the limit as n goes to infinity of n over n plus 1. And that limit is 1. So this is the absolute value of x times 1. Now I have to get convergence, this limit has to be less than 1, which means that if the absolute value of x is less than 1, then x has to be smaller than 1, right, or bigger than -1. Anything between -1 and 1 will have an absolute value that's smaller than 1. And then I have to test the endpoints separately. So this is my open interval of convergence. The endpoints are open. And now I need to determine, do I close one or both or neither endpoints? So let's test x equals -1. So I'm going back to my closed form here. I'm going to replace x with a -1. So I have the sum of -1 to the n over n times -1 to the n plus 1. So I just replaced the x with a -1. Now, -1 to the n times -1 to the n plus 1, that is -1 to the 2n plus 1. And I'm starting at n equals 1 to infinity. 2n plus 1 is always odd. Plug in a 1, you get 3. Plug in a 2, you get 5. Plug in a 3, you get 7. So I'm raising 1 to odd powers, and -1 to odd powers, which is always going to give me a -1. So this is the sum of -1 over n. Always -1, so this would be like -1 minus a half minus a third minus ... And that is the harmonic series. That's a p series. Could factor out a -1, and this would be 1 plus a half plus a third plus a fourth. And that is a p series where p equals 1, so this diverges. Okay, so I am not going to add an or equal to on the -1. All right, let's see what happens when I plug in x equals 1. So this gives me the sum from n equals 1 to infinity of 1 to the n over n times -1 to the n plus 1. And 1 to the n is just 1, no matter what n is. So this will be the sum of -1 to the n plus 1 over n. So if I write down a few terms of this, I'm going to get 1 minus a half plus a third minus a fourth plus ... And this is the alternating harmonic series. This converges by the alternating series test, which means that I'm going to close my interval at 1. So looking at my interval of convergence, -1 to 1, I'm going to add an or equal to at the 1. So my final interval of convergence, -1 less than x less than 1. The ratio test told me that. And then I tested each endpoint separately, and I saw that it converged at 1. So I'm going to add an or equal to there. Okay, to find the Taylor series expansion for f of x equals x times e to the x near x equals 0, really call that a equals 0, we follow this process. So I'm going to find 6 derivatives and evaluate them at 0. So my function is x times e to the x, which means to get f prime, I have to use the product rule. First times the derivative of the second plus the second times the derivative of the first, which is 1. Not even going to write it. And then to get f double prime, I need to use the product rule on this. So I get x e to the x plus e to the x. And then the derivative of this is e to the x. Do it again, and I get x e to the x plus e to the x. And then I still have these two e to the x's to take the derivative of. And then do it again, and you get x e to the x plus e to the x. I had 3 e to the x's up here I need to take the derivative of, so I have 3 e to the x's. See, x e to the x plus e to the x. And then I have 4 e to the x's above that I need to also carry over. All right, one more time. The derivative of x e to the x is x e to the x plus e to the x. And then I still have all of these things to take the derivative of, which ends up being 5 e to the x's to take the derivative of. Okay, so I'm going to plug 0 into all these derivatives, and 0 times e to the 0 is 0. And then I get 0 plus 1, and then 2, and then 3, and 4, and 5, and 6. And now I'm going to plug all that stuff into my formula for the Taylor series. So f of a, that's f of 0, so that's 0 over 0 factorial, times x minus a is 0 in this case, so this is x to the 0. F prime of 0 is 1 times x to the first. F double prime was 2 times x squared. F triple prime is 3. The fourth derivative is 4. And the fifth derivative is 5. Okay. So we've written down 7 terms. And now maybe I'll just simplify them a little bit. This is 0. This first term is 0, so that goes away. And then I have x plus x squared plus, okay, so 3 over 3 factorial, that's going to simplify to 2. 4 over 4 factorial, that simplifies to 6, because that's 4 over 24. And 5 over 5 factorial, that simplifies to 24. Six over 6 factorial is 120. Okay, so to find a formula for the general term, let's see. I should recognize that 2, 6, 24, and 120, those are factorials. So this will be 1, oh, whoops. This is over 1, and this is over 0 factorial. So my general term, all of my terms are x to a power, the first, second, third. So let's start n at 1, and I'll say they all have x to the n. And then the denominator is a factorial, 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial. These are all factorials that are 1 less than the exponent was. So this, take 1 from the exponent and do a factorial. Okay, to find the interval of convergence for this series, ratio test. Limit as n goes to infinity of a sub n plus 1 over a sub n. And whatever this comes out to, we're going to force it to be less than 1. We get convergence when this limit is less than 1. So let's see, the n plus first term, replace all my n's with n plus 1's, and I get x to the n plus 1 over n plus 1 minus 1 is n. And then divide by the nth term or multiply by its reciprocal. Okay, n plus 1, x to the n plus 1 over x to the n simplifies to x. And then n minus 1 factorial over n factorial reduces to 1 over n. Take the absolute value of x out of the limit. And the limit as n goes to infinity of 1 over n is 0. So this is 0, which is always less than 1 no matter what x is. So my interval of convergence is negative infinity to infinity. All x's will lead to a limit that's less than 1. So interval of convergence is infinite. Okay, let's look at these non-sigma versions for the Taylor series for x e to the x. We did a lot of work to get this one. We took 6 derivatives and built the whole thing from scratch. But if you look at e to the x, they're really close. And another way that I could have found the Taylor series for x e to the x would be to multiply x by the Taylor series for e to the x. Okay, and when you distribute the x, you get x plus x squared over 1 factorial plus x cubed over 2 factorial plus x to the 4th over 3 factorial plus da, da, da. Okay, so here's another one. We're going to get the Taylor series from scratch. I want the Taylor series for sine of x at a equals pi over 4 by following this process. I'm going to take 6 derivatives of sine x, and I'm going to plug pi over 4 into all of them. So f of x is sine x. The first derivative is cosine x. The derivative of cosine is negative sine. The derivative of sine is cosine, and there's a negative in front that comes along. The derivative of cosine is negative sine, and there's already a negative in front, so it becomes positive sine. And then they repeat. Cosine, negative sine. Plug in pi over 4. So it might be helpful to be glancing at a unit circle here. Pi over 4 is right here. The coordinates of that point are root 2 over 2, comma root 2 over 2. So the sine is the y coordinate and the cosine is the x coordinate. So sine of pi over 4 is root 2 over 2. Cosine is root 2 over 2. The negative sign is negative root 2 over 2. Negative cosine, then the sine, root 2 over 2. Cosine, root 2 over 2. And negative sine is negative root 2 over 2. Now I'm going to plug all of those f and f prime values into this formula. So f of 0 is root 2 over 2 over 0 factorial times x minus pi over 4 to the 0. Plus the first derivative at 0 was root 2 over 2 over 1 factorial times x minus pi over 4 to the first. It says I'm supposed to write down the first 7 terms, which means I need to go to the 6th power here because my first term had a 0 power. Okay, f double prime of 0 was negative root 2 over 2. So I have negative root 2 over 2 over 2 factorial times x minus pi over 4 squared. Triple prime was also negative. Okay, the fourth derivative was positive again. And the fifth derivative is positive, root 2 over 2. And then the sixth derivative is negative root 2 over 2 over 6 factorial times x minus pi over 4 to the 6th. My next derivative would be negative if I follow this pattern. I've got positive, positive, negative, negative, positive, positive, negative. My next one's going to be negative again, dot, dot, dot. All right, you could leave it like that, or we could simplify it a little bit by factoring out a root 2 over 2 from every term. So factor out root 2 over 2. And that would leave me with 1 over 0 factorial, which is 1. And then I have this piece to the 0, which is 1. So my first term here is a 1. And then my next term, after I have factored out root 2 over 2, I have x minus pi over 4 over 1 factorial. And then I have, so that was positive, positive. Now I have minus x minus pi over 4 squared over 2 factorial. Then another minus x minus pi over 4 cubed over 3 factorial. And I switch back to plus x minus pi over 4 to the 4th over 4 factorial plus x minus pi over 4 to the 5th over 5 factorial minus x minus pi over 4 to the 6th over 6 factorial plus dot, dot, dot. All right, so if I want to write this in sigma notation, this is root 2 over 2 times the sum. And every term looks like x minus 4 to a power. x minus pi over 4 to a power. So my first power is 0 because this one term is actually an x minus pi over 4 to the 0 power. The denominator is a factorial. My first one is a 0 factorial. So oops. So make this n and make this n factorial, and we're going to start n at 0. And the direction said don't worry about the negatives when you write the general term. Okay, good. I didn't want to. Oh, I was also supposed to find the interval of convergence. Okay. So the reason that the negatives don't matter, I mean, they matter, but what I need is, I shouldn't have written this. I'm just going to write that this is the general term. So it's not actually equal to the sum because I didn't account for the changing signs. But I only need the general term in absolute value to do the ratio test. So if I do the ratio test on this, I would take the limit as n goes to infinity of the n plus first term, which is, I'm going to leave the root 2 over 2 out. So this is just going to be x minus pi over 4 to the n plus 1 over n plus 1 factorial. And then divide by the nth term or multiply by its reciprocal. And I can ignore all the changing signs because this is all an absolute value. All right, so this becomes the limit as n goes to infinity of x minus pi over 4 in the numerator. And then n factorial over n plus 1 factorial is 1 over n plus 1. And this limit is going to be 0. Because 1 over n plus 1 as n goes to infinity, that goes to 0. So this is always less than 1, which means that my interval of convergence is negative infinity to infinity. It does not matter at all what this x value is. The limit will always be 0, which is always less than 1. Number 4. Okay, here's the Taylor series expansion for sine x centered at 0, at a equals 0. I want to take the derivative of both sides and see if we can come up with a Taylor series expansion for cosine x without having to start from scratch. So the derivative of sine is cosine, and then I'm going to differentiate term by term. So I get 1 minus 3x squared over 3 factorial plus 5x to the 4th over 5 factorial minus 7x to the 6th over 7 factorial plus 9x to the 8th over 9 factorial minus dot, dot, dot. And then I can simplify the coefficients. 3 over 3 factorial. 3 factorial is 3 times 2 times 1. So that leaves me with 2 times 1, which is 2 factorial after I cancel the 3's. And then 5 over 5 factorial. 5 factorial is 5 times 4 times 3 times 2 times 1. Cancel the 5's, and you're left with 4 times 3 times 2 times 1, which is 4 factorial. And then this is just going to keep happening. I get x to the 6th over 6 factorial plus x to the 8th over 8 factorial minus dot, dot, dot.